And as we are doing this transition, I'll read the brief introduction for Trevor. Dr. Bazat is an assistant teaching professor at the University of Victoria in Canada. He completed his PhD in the field of algebraic topology at the University of Toronto. He's a passionate advocate for mathematical literacy in society and shares his excitement for mathematics in both his classrooms and globally on his public YouTube channel. We're honored to have him join us today. So with that, Dr. Bazat.
Hello, thank you. And thank you both to ILSI for this wonderful opportunity. I wasn't aware of this organization and before Gwendolyn contacted me, but now that I had this opportunity, I've sort of investigated the organization. I've been really impressed with the wonderful work that you do. So thank you for this opportunity and thank you for the work that you do. And thank you for everybody who's listening. We're in challenging times right now. And this topic that Jason and I are going to talk about, there's some natural interest in it. And as mentioned, I'm interested generally in society of people having sort of quantitative literacy and mathematical literacy. And I think that this topic is an excellent one for that. As mentioned, I'm a math professor. And when I say that to people, there's different types of reactions they have. You might want to reflect on what your own reaction to that is. And there's two types of reactions that I hear over and over and over again, whether it's random people I meet or students or commenters on my YouTube channel. One comment that they say very often is, I'm bad at math. And I don't know if you're sitting there and sort of nodding off. Yes, I feel like I'm one of those people who's bad at math, perhaps not. If that is you, well, I disagree. I don't think that that's actually true, but okay. The other one, however, maybe rubs my gears wrong, even somewhat worse, is the idea that, is math really useful? I mean, you have to use math to compute a tip, for example, but beyond that, is there any real need? Or maybe you acknowledge that there's need for the specialists at Google or, on Bay Street or something like this, but for individuals within society. And so this is an issue that as a math professor, I confront all the time in my, say, first year calculus courses. Why should the students be there? Is it really useful? And while we're in extremely challenging times right now, one of the things that has sort of come out, I sense at least, is a greater understanding of the value of mathematical literacy within society. For example, the concept of exponential growth, a concept that we're all now perhaps too familiar with. The fact that we can understand that concept and communicate that concept and share that concept, not just among a few experts, but widely, is what builds the sort of social pressures to be able to obey things like social distancing, which of course puts a lot of costs on our lives, but nevertheless is very important. So I hope that there's that small positive of a result of this very unfortunate crisis that we find ourselves in. I actually teach a modeling course at the University of Victoria, a third-year course that the goal of which is to take real-world problems and use math to actually model that. And I was so proud this semester that the students in their final projects, a large portion of whom they could choose anything they wish, chose to model COVID-19 or epidemics in general and see all the different ways that students could dive in, and people are really engaged in the subject. All right, so let's go into it. I'm going to talk in this particular talk about mathematical models. We're going to do a little bit of math in this particular talk. And my goal here is a broad foundation as the types of ideas that go into mathematical modeling and the ways that we can come up with and analyze mathematical models. And indeed, I'm not going to really focus too closely on the specifics of COVID-19, the exact data of COVID-19. I want to lay the foundation behind the ideas that go into modeling, well, just spread of diseases in general. And the first point I want to do is what's on this slide, is to think about the modeling process as having a few different phases. An assumption phase. The assumption phase is where you write down whatever it is that you believe is true about this thing that you're studying. Or perhaps it's the list of things that you believe are true that you're capable of writing down into some sort of mathematics model. Assumptions are something that you and I could debate. in plain language. We don't necessarily need to have high levels of mathematical sophistication. We could debate, for example, whether or not asymptomatic carriers of COVID-19 exist. This is something that the consensus changed on. Now we understand that there are these things. So assumptions are very important. And then there's a second phase, a phase that I will call the model derivation. This is going to be kind of the good math phase. This is the part I like, at least. This is where you write down equations that reflect mathematically the assumptions that you've made. And then after you've got these equations, okay, well, equations just sort of sit there. You have to do something with them. And indeed, you can go to a phase which is sort of analysis phase, and you can say, well, what can we learn? We've put in these assumptions, but what's this new result that we can get? What can we be motivated by? For example, you could see that COVID-19 may lead to, if you do not have any actions like social distancing, could lead to enormous numbers of cases. And that's some very important sort of analysis that you can get out of these things. But one word of warning, and I just sort of do this sort of brief overview, is that a model is only as good as its assumptions are. If you have bad assumptions, you can have the most brilliant mathematical model in the world, and its results may be absolutely useless. And likewise, you can conclude whatever you like with a mathematical model. You want to conclude something interesting? Well, some way you can build that into the assumptions, and you will be able to conclude whatever you like. So a model isn't necessarily right or wrong, but it presents a way of understanding the world. All right, so with that basis, let's try to think about one way that we could try to model the spread of an epidemic. And what I'm going to introduce here is called a compartment model, SIR model, or SIR model is our first one. And the way it works is this. It imagines, take all people in the world. I'm going to divide them into a few categories. The first category is called susceptibles. Susceptibles are the people who are capable of getting the disease, which for COVID-19 is still most of us. Most of us are still susceptible to it. And I write S of T here in the name. I'm going to have this shorthand. You're going to see S of T appearing a lot as we go into the future. And it just counts the number of people who are susceptible at some particular time T. Well, that's not everybody. Unfortunately, there's also these infectious people. So people who have gotten the disease and have not yet gone and been recovered. So these are people who are capable of spreading it to other people. So some susceptibles will move into this infectious stage, and then you can move along into a recovered stage after that. So we have a susceptible, infectious, and recovered stages. And the idea is that every one of us listening right now is in one of these three cases. I talked about how we think about what our assumptions are, and then we build a model out of it. Well, this diagram is meant to list what some of my assumptions are. I'm saying there's three categories, not 4 or 5 or 6, although we'll talk about what other possibilities there might be later. And I'm saying with these arrows that they only go this way. So for example, a really interesting one that we're gonna have to talk about later is, what about if recovered people can transition back? Could there be an arrow where they could become susceptible? But nevertheless, these are the assumptions we're gonna make right now. Okay, let's talk about a few other assumptions we're gonna make. I'm going to assume the statement S of T plus I of T plus R of T is equal to N. What I mean by this statement is that if you add up everybody, namely the susceptibles, the infectious and the recovered, what you get is this value of N, and N is just my shorthand for everybody in the world right now. I'm gonna make some simplifying assumptions. I'm gonna assume, for instance, that there's no births. I'm gonna assume that there's no natural deaths, just to keep this model simple. And well, there may be deaths due to the disease. You may have noticed I previously called R recovered, perhaps a bit euphemistically. If unfortunately someone was to pass away, then from the perspective of the model, maybe you'd like to refer to it as removed people. They are people who are not able to infect somebody. So while this distinction, of course, is very, very important to somebody who's infectious, you need to know which category you're going to end up in. From the perspective of the model, it treats them both the same. The other thing I want to consider in this model is I want to refer to something called initial conditions. Initial conditions are what happens at time T equal to 0. So T equal to 0 could be, for example, if you had some town, I'm going to talk about a fictitious town a little bit with 5,000 people. you could imagine that at time t equal to 0, you get your first few cases. S of 0 refers to the initial number of susceptible people. I'll give it the name S sub 0, or sometimes I call this S naught. Just refers to the number of people who are initially susceptible, which is most of us. The number of people who are initially infectious, which is perhaps just one, or maybe the first time you observe it, it's a small number, 10 or something like that. It's a small number, and then we'll just assume that nobody's been recovered. So basically, I've specified what happens at the beginning. And what I want to know is what happens as time goes on. I want to know, what is that S of t? What is that I of t? What is that R of t? How does this develop? So I want some equations. And what I'm going to do is study something slightly strange, not Si and R. I'm going to call it S prime, I prime, and R prime. And the idea of that symbol is to indicate a rate of change. So for example, I might be interested in what is the rate of new infectious people per day, or conversely, what is the rate at which people leave being susceptibles per day. So when I have these little primes up here, I mean, some of you will know that this refers to derivatives in calculus, but that's not relevant for this talk. What the primes indicate is that we're not talking about the variable itself. We're talking about how that variable changes in time, the rate of change per day. And indeed, this is something that mathematicians really like. They love rate of changes because that's the way data comes to us. You often know, for example, that you're saving $100 per month. And so you can use this rate that's being told to you to influence, how much money you're going to have as time goes on. Likewise, we get this reporting data per day, and so these rates of change make sense. So what I want to try and think about is let's focus in on what should I put here for my S prime. Well, I'm trying to figure out what would the rate of change of susceptible people. The susceptible people are going to get infected, and how would they get infected? Well, the way someone would become infected be that there'd be some interaction between somebody who was susceptible and somebody who was infectious. Perhaps the infectious person coughs on the susceptible person, or the infectious person touches something that the susceptible person touches shortly afterwards. It's interactions between susceptible people and infectious people that result in someone transitioning from susceptible to infectious, that result in a rate of change. So let me conjecture this as a possible thing to write down for S prime. What you'll notice is that there is a product of S times I, and this S times I think of as the interactions between S and I. If there's a large number of S and a large number of I, then S times I will be a large number. If I was 0, then S prime would be 0. The rate of change would be 0. If there was no infected people, there'd be no change. Likewise, if there was no susceptible people, if everyone was infectious, that's not hopefully going to happen, but if that was the case, then indeed you would also get 0. But if you're in the middle somewhere where there is a lot of infected people and a lot of susceptible people, then the S times I would be very, very high, and you'd have a large number of people transitioning to this infectious state. What's that little A? A is a constant. It's a constant proportionality. It's a positive constant with a negative sign out front of it. And the negative sign is there because if you think about what's happening, well, there's less and less susceptible people as time goes on. As time goes on, more people get infected, less people are susceptible. And thus this rate of change that we have has this particular behavior that this S prime is a negative value. All right, so that's my introduction to S prime. What about I prime? Well, how do you get someone infected? If someone had just left the susceptible case, it means they've just entered the infectious case. So this minus ASI, which is people leaving the susceptibles, if I want to figure out what happens here for the infectious, it just gets added back in. All of those susceptible people are transitioning into infectious people under the assumptions of this model. But that's not it. We also are going to have the possibility that people who are infectious can then become recovered as some time goes on. So I need to add a term for that. So I'm going to modify my I prime, and I'm going to subtract a second term called minus BI. And notice that minus BI, this is now a constant B, multiplied to the number of infectious people. Oh, why might that be? Imagine that you're currently infectious, and perhaps some proportion of the infectious people per day are becoming recovered. Maybe 10% of the infectious people, say today, just to make up a random number, are transitioning from the infectious to the recovered. It doesn't matter how many susceptible people are. So this is not multiplied times SI, it's only multiplied by I. It's a little bit like when you talk about a bank account and you're trying to figure out, well, what is the rate of change of my bank account? Well, it might be, say, 5% interest multiplied by how much money you have in the bank account. So rates of change is some number times how much you have. And the same story here. The rate of change of the infected people is this negative BI. Okay, well, you lose that from the infectious state. What happens? We have to add that back into the recovered state. So the minus BI gets added back in, and so you have this negative there and this plus there. So these two terms are sort of paired up, and those two terms are paired up there. And so what we have here, this is the SIR model. This is going to be our base. We want to do some analysis of this model. And we want to see how we can expand this model, tweak it, add other factors that we haven't done. This SIR model, by the way, is sometimes referred to as the Kermack and McKendrick model for the people who originally came up with it, or the SIR model. The fancy name for this type of model, this class of modeling, is called a system of differential equations, which is a big, long, fancy buzzword. Basically, it means it's got equations that involve rates of change, these primes in it. And by system, what we mean is that more than one equation is happening, and that they're all true at the same time. We're all sort of interlinked. It's this equation for S prime involves S, but it also involves I, and the I also involves S, and the R involves the I. They're all linked together, and that is what a system of differential equations is. It's a very powerful piece of mathematics. Okay, so then you might ask, now we're going to transition it in our simplest example into the third phase of our modeling process. We talked about assumptions. We derived our model. Here it is, these equations. Then you're going to ask, well, what's the analysis phase? What can we get from this? How can we learn something from these equations that we've just written down? What's that connection? So what we're going to do is we're going to solve this numerically. So what I've done here is created a toy model here. I made a fictitious town. My fictitious town has 5,000 people in it. And it's the spread of a disease that happens over a time period of 60 days down here. So on the bottom, we have time, we have population on the vertical axis. And in this case, I want to make it visually nice. But the consequence of making it visually nice is this is a disastrous situation. The recovered people, which is what the blue is, if you trace along those blue curves, it starts down at 0, which makes sense at the beginning. And there's no recovered people right at the beginning, then it goes along, and then it gets up to, just under 4,500 of them. So this is a disease. This is something we absolutely do not want to have happen. This is a case where almost everybody has gotten this disease. And the reason why it's so high is based on my made up choices of constants down here. Remember the key thing in our model that we saw previously, when we look back, which was just the constant A and a constant B. Well, I just made up some values of these. So B equal to 0.2 would represent 20% of the infected population per day transitioning to being recovered. You might observe the A is a really small number here. Well, that sort of makes sense because the A was the coefficient of S times I, which could be very large. So for example, if I look say around here, it looks like 3,000 of the susceptible people and about 1,000 infectious. So you multiply S times I, you're at 3 million. Multiply that by 0.001, and that would give you 300 per day. So that would be in this fictitious town, 300 per day would be getting infected at about this time. I can put up the three equations that we had that were governing these equations that govern the rate of changes. I think that the graphs hopefully make some sense. For instance, recall that the rate of change of the susceptibles, this S prime here, was a negative value. And that meant that the susceptibles were always losing people. And indeed, if you plot this out, what you see is it comes down, 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 down. It's always going down. Likewise for the recovered's got this positive B. It's always going up, and indeed it does. Up, 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 up. Those are the recovered people. And then the tricky one is the infectious, because the infectious has a prime here, so there's a positive and a negative. And so I have a positive and a negative resulting, and as a result, it's sometimes going up and sometimes going down. Okay, so let's change the numbers around a little bit. Let me imagine that we try to do a better job of this, and our A is smaller. Okay, so I made it not 0.001, I made it 0.0006. And now you can barely see it, so I'm actually gonna take the 70 that we have down here, and I'm gonna stretch it out and make it a 140 so we can see everything. And what you notice is that by changing the value of this coefficient, now the recovereds plateau off at a little under 3,000, which is still disastrous, but much better than it was before. We could go again if we wished. Okay, I drop it down to 0.00005. It's now dropped under 2,000. And we could choose just lower and lower values of A if we so wished, effectively by taking this infected, and it would be so flattened it would be hard to sort of demonstrate graphically. So nevertheless, we have these nice diagrams. Okay, so I want to recall that the I prime was the one that was weird, that went up and then went down, that had the positive and the negative. That's the one I want to study a little bit more. So let me just focus just on that I prime. This is the rate of change of infectious people. By the way, the first number, ASI, this is what we get reported in the news every day. You find out that in, I live in British Columbia, for example, you find out that in British Columbia, say 26 new cases appeared. Well, technically what we're modeling when you get that is how many cases have been actually measured by people who've taken the test. Of course, there's presumably more cases that have not had the test, but nevertheless, that's the new cases, and then you subtract off people who leave and go into the recovered category. Nevertheless, what I really want to know is there going to be an epidemic or not? Well, we know the answer now, but at any given time, we want to know, is there going to be an epidemic or not? And so what I want to know is, if I look at time t equal to 0 at the beginning, I prime of 0. Remember, we called S of 0 S naught and I of 0 I naught, and so we plug those numbers in. The question is that rate of change less than 0 or more than 0? If it's positive, what we're saying is there's an increase in the number of infected people, we get an epidemic. If it's less than 0, then we don't. So we really care about this particular quantity. That tells us the most important thing is there going to be an epidemic or not. I see there's an I naught on both sides. So what I'm going to do is just cancel out that I naught. It's just some number. I'm just going to divide out by it. So this is really asking just as AS naught minus B less than 0. I can take the B, I can move it to the other side. I can divide out by the B. I would leave a 1 on the right-hand side. And this leaves me with, is AS naught divided by B less than 1? So by moving the B to the right-hand side, it creates this 1 on the right-hand side. So that's the thing I'm interested in. The question of, is there going to be an epidemic, comes down to this. I just copied and pasted it, but color-coded it now. AS naught over B. This is sometimes referred to as the basic reproduction number. R naught, by the way, not to be confused with the number of recovered people initially. It's called the basic reproduction number, sometimes basic reproduction rate, but reproduction number is better in this context. And it has these 3 different parameters. So one of the things we want to look at here is the value of the A, which, if you remember, refer to the number of susceptible people becoming infectious. The S naught, which is the initial susceptible population, and finally the B, which is the rate which infectious people become recovered. So then the question is, well, what can we do about this? Like, what kind of public health things can we do to affect these different things? And the different types of things you've heard about all fall into one of these different categories. So for example, social distancing, that's the big one we're doing right now. Social distancing is a way of making the rate of which susceptible people become infectious smaller. It takes the coefficient of S times I, it makes it smaller. Likewise, washing your hands, likewise, not touching your face, likewise, wearing a face mask. All of these different things are techniques to lower that value of the A. The smaller it is, the better the chance that it drops underneath 1, which is when things become good, when things go away. Initial susceptible population, oh, that's a hard one, but we have one technique for many diseases, but not yet for COVID-19, which is vaccination. We can reduce the proportion of people who are initially susceptible to disease by vaccinating. This is how we combat many different types of extremely infectious diseases. We just don't have that yet, and won't for a while with COVID-19. B is a little bit harder to manipulate. So this is people who are sick. One sort of funky way to do it, I mean, you can do better medicine to try to heal them faster, but quarantine. Quarantine's sort of a funky way of calling someone recovered. They're of course not recovered from their own lived experience. They're still suffering from this disease. But from the perspective of them being able to infect other people, other than possibly the medical staff who's around them at hopefully a low rate, we do our jobs well, that nevertheless they can be treated sort of somewhat as pulled outside of the population. And so quarantining people is a good way to get this B number to be larger. You're taking people out of the infectious category faster, and larger numbers on the denominator make it smaller overall. All right, so that is going to give us some types of ways we can affect this basic reproduction number, the core question of whether we get an epidemic or whether we don't. One thing just for people who are sort of aware of exponential growth, we talk about it all the time. Where does it come from? If I look at this equation, this I prime, which I will allow I to vary to be a parameter, but for S, I'm just going to assume that near the beginning, S naught is a constant, it's so large, it's almost everybody, I'll think of it as a constant. So I'll just keep this out the front. And then there's a way you can actually analytically solve this thing. And again, it's fine if that's not your cup of tea, but it can be analytically solved, and it gives this exponential growth. So the exponential growth is what we see. And let's go back to the graph. If I look at infectious people over here, then what I have is that as I track along the green in the initial period, that was my assumption in my previous calculation, in this initial period here, you're going to have these infectious people, and it's going up much like an exponential curve. And indeed, it was almost shocking to me, even though I understand at some level how these things work, it was almost shocking to me how in every country in the early period, country after country, it was obeying an exponential growth so clearly. And then as time goes on, it will transition away, and these recovered people obey what we call logistic growth, where it's sort of exponential at the beginning and goes up. Okay, so now you might wonder, well, what do we do if we are going to have social distancing? Well, if you do social distancing, then I'm going to imagine that I'm going to impose it sometime. So here's what I've done. At this time of it looks like t equal to 25, I ran my little program that generated these graphs for the first 25 days, and then I stopped it, and I said, let's change the value of A. It's no longer 0001, it's 4 zeros now, 00002. And then I will let the program now run again from that new constant. As you can see, everything sort of flattens out really, really quickly in this idealized case. And so indeed, the number of people who end up being recovered, that means who have gotten this, is much smaller than it was previously. So that's the good news. That's why social distancing works. You can see it very dramatically. But here's the bad news. We do social distancing for a little while and then turn it off. Well, what happens here? Okay, so this is a new version. It's gotten stretched out. I've gone up to 100 days so we can show everything. In this toy model that I'm talking about here, we go in the first little while, and I just do the normal value of A, and then we do social distancing for a period in the middle between 25 days and 45 days. And there it looks pretty good. Things flatten out, things are going good. But after 45 days, we turn it off and we stop social distancing. This is the supposition of this particular toy model here. If we do that, then what's going to happen? As you can see, these recovered growth rates, they grow back up and they start building up again. Just speaks somewhat to the importance of getting a vaccine at some point, because at the end of the day, this pattern continues. When you relax social distancing, you should expect some level of growth again. Now, notice the growth has different characteristics. Again, I'm choosing outrageously large numbers, so it looks good here, but in this initial period, you have it really spiking very steeply, and you get this spike here until we turn social distancing on. There is another spike here in the second phase, but it is a much, much flatter one. And that's because instead of the full 5,000 being susceptible, now the susceptibles have dropped down to only a little over 3,000. So when people interact, 2,000 of them who have gotten the disease in this toy model, they're removed from consideration under the assumptions that we have. All right. So When I think about the 3 steps that we've done here, the portion which is thinking about the assumptions that are built in, the writing down of equations, the model derivation, and then finally moving on towards the analysis phase of it, it strikes me how almost overly simple we've been so far. And that's true. That's what we should expect at this phase. There are many assumptions that we have not even talked about. 3 different categories, for example. Perhaps there's more, and many versions of these models take other categories. Maybe you want to stratify by age. You want to consider the effects of vaccinations. How exactly is that going to affect things? There's an enormous number of factors that we're not even considering. And indeed, this model is completely blind to any number of things like urban density and different sort of strategies with different countries and things like hospital capacities. None of this is built into this model, but nevertheless, I hope it gives something of I don't know, I suppose an overview of what we can expect. Okay, so I'm just going to jump to my final slide here just to say thank you once again. I hope you enjoyed this introduction, and I look forward to your questions at the end.
Great. Thanks so much, Trevor. That's absolutely fascinating. I think we're all reflecting now on what you shared about the math and how that's actually impactful to all. Give an introduction for Dr. Kindrachuk. He's an assistant professor in the Department of Medical Microbiology and Infectious Disease at University of Manitoba, Canada. He holds a Tier 2 Canada Research Chair in Molecular Pathogenesis of Emerging and Re-emerging Viruses. He has broad experience and expertise in emerging viruses and pandemic outbreak preparedness for both developing and developed nations. Importantly, he actively participates in multiple international scientific outreach activities to provide training and expertise to regional partners in Africa, including Sierra Leone, Gabon, and Kenya. Dr. Kindrachuk's research program focuses on investigation of emerging virus circulation, transmission, and pathogenesis. In particular, his work focuses on those viruses that pose greatest threat to global human and animal health, including Ebola virus, influenza virus, and coronaviruses. From his investigations, they will help inform emerging virus therapeutic treatments, strategies, outbreak predictions, and preparedness. Dr. Kindrachuk has served on multiple expert committees with the World Health Organization and also as an associate editor with multiple scientific journals and a scientific contributor with Forbes. He actively participates in interviews with local, national, and international media on a broad range of infectious disease topics. So we're very fortunate to have Dr. Kindrachuk join us today. And with that, please, sir.
Great. Thank you so much, Wendelin, and thank you as well, obviously, to Ilse for the invitation. It's always tough going second, especially when you have somebody that is unbelievably smart and talented going ahead of you. I will put the disclaimer out. I am just a simple virologist, so I hopefully can give some context to the current situation that we're in with COVID-19. And hopefully share some of my expertise and experience on what the situation is and where we're going. So I'm going to just quickly change this over to laser pointer. All right. And so I always start off my talks with essentially the exact same slide. And so this slide was produced by Dr. David Morans at NIAID, National Institutes of Health. I worked with basically alongside David for a couple of years. Another disclaimer, I actually used to be at NIH for about 8 years prior to coming back to Canada to take my faculty position. But David has done a remarkable job over the years of essentially updating this figure, talking about emerging and re-emerging infectious diseases and essentially the global burden. And what we basically know as researchers is that over time, what we're seeing is that we're facing an increasing burden of the emergence of these diseases. And I don't want to start off my talk always with doom and gloom, but the simple fact is that we are really fighting, a battle that we are never going to win. Viruses and bacteria and parasites and really every pathogen under the sun has been evolving for eons longer than we have, and they are extremely efficient and extremely good at what they do. What we can do is try to essentially try to contain these pathogens or restrict their movement and their transmission. And sometimes we do that really well, and sometimes not so well. I also usually put this slide up just to give some context as well for the things that I've been involved with in the past. So it's a growing list. I worked a lot with really high containment viruses across the board, predominantly with Ebola, but multiple influenza viruses, including H7N9, H5N1, and 1918 virus. But I worked a lot with coronaviruses as well, and that includes both MERS and SARS coronaviruses, as well as SARS-CoV-2. So the form of this talk was presented by me in fall time of 2019, and I put the slide up, and I had kind of debated back and forth whether I was going to put it up today. But I think it's important. It's important for us to discuss some of the limitations that we know that we continually face with infectious disease and pandemics. So the World Health Organization, or WHO, helped create basically a global preparedness monitoring board. And this global preparedness monitoring board was essentially created to look at our overall level of preparedness for emerging and re-emerging health emergencies and public health risks. And what they essentially found was that ultimately we were unprepared and have been vastly unprepared for incoming pandemics. And I think that, seeing what has happened and transpired over the last 5 months, it's obvious that we still are vastly unprepared. Though we are able to respond quite quickly, we're not in a good position right now to be able to predictive research what viruses are coming or what pathogens are coming down the pipe, but also in terms of just things like overall supply chains across the globe, and being able to mitigate potential interruptions and disruptions in those. So really the Global Preparedness Monitoring Board had identified 7 urgent actions that they felt were needed to prepare for world health emergencies. And I really think the top 4 are kind of where I fit in, and maybe where I've moved from being just a guy that likes to play with viruses in the lab to somebody that is advocating much more on an international level for our preparedness. And it really comes down to the fact that heads of government across the globe, and that includes in low and middle income countries, which are disproportionately affected by these types of emerging infectious diseases, that there has to be a commitment to basically invest and prepare for all regions of the globe. I think particularly now, because we are so interconnected just through globalization, we don't really have the ability to act as isolated entities anymore. We basically, from 1918 onwards, we know that has not been the case, and I think we have to appreciate that what happens on one very tiny section of the globe at this point can have massive ramifications very, very quickly. We know that countries and regional organizations have to lead by example, so we need people across the board to be ready to step up to the plate when we need leadership. Countries need to build strong infrastructure systems. This is particularly important within low and middle income regions, again, because like I said, they are disproportionately affected by emerging infectious diseases. And I think my best example of this is the work that I do currently in Africa, and primarily in West Africa. I was on the ground during the West African Ebola epidemic, leading diagnostic efforts in Liberia. I spent a lot of time in Sierra Leone now, and what I can say pretty comfortably is that I don't really feel as if those regions are any more prepared for basically infectious disease outbreaks than they maybe were 6 years ago now. And really, countries, donors, and multilateral institutions across the globe have to prepare for the worst. I think we have to kind of move away from just assuming that that things will be bad, to actually assuming that things will be quite horrible. And we need to understand that we are not just dealing with things like mass casualties. So we have to start to have a better appreciation for just the devastating effects that these types of events will have on things like food safety, as well as obviously global economies. So where do I fit in this? Basically, I run essentially what I term, or what people have termed, One Health, looking at emerging viruses. And when I talk about One Health, what I'm really talking about is this interface of essentially humans and animals, but their environment. So trying to understand essentially how viruses move between different animals, including humans, and how that movement is actually related also to the external environment. So things like changes in temperature, or changes in precipitation, or changes in urbanization. How can we start to understand all these variables and the roles that they play in basically spillover events of viruses into either wildlife or into humans? And this is really based out of, predominantly, like I said, out of Africa. So West Africa and Sierra Leone do quite a bit of work now in Central Africa, mostly in Gabon and Republic of Congo, but a little bit in DRC. We're getting involved with some work primarily on gorillas in Rwanda. And then I was actually most recently in Kenya for 3 weeks in January, leading an emerging virus science outreach program to try and help build local capacity. So with that and kind of that background, let's jump into the thing that you're all probably here for and probably the most interested in, which is this this new beast that we are facing called COVID-19. So let's just talk about a quick introduction to coronaviruses, because I think it's something that maybe we don't give, or us, me and others as scientists, we don't give enough credit to when we do media interviews, is the fact that while SARS coronavirus 2, which is the virus that causes COVID-19, while that one is novel, coronaviruses have been around for a long time. They're a massive family of viruses. They have an RNA genome, so it's a single-stranded positive sense RNA genome. It's actually fairly, it's not as error-prone as other RNA viruses, and that actually has to do with basically a proofreading activity within the polymerase for the virus. So basically, as the virus makes more copies of itself, it's able to basically do a quick proofread or a spell check as it goes through and starts recreating those viral genomes. And that leads to a reduced rate of mutation within these viruses. There are multiple subfamily members, and we now know that there are 7 coronaviruses that cause diseases in humans. Basically, 4 of these have been circulating in the population since, some probably in the 1960s. They predominantly are related to very mild or cold-like illnesses in humans. They're endemic in the human population. And really, they were the reason that nobody really paid any attention to coronaviruses for a long period of time. The coronas just were not, really seen as being, a virus that was going to impact global public health. And although we did see some cases of severe respiratory illness, those were predominantly in children that were, compromised, or as well in seniors that had underlying health conditions. That all changed though in the early 2000s. So 2002, we saw the emergence of SARS coronavirus within China, which ended up being an epidemic that stretched across the globe. And then we saw a subsequent emergence of MERS coronavirus in 2012, which continues to cause isolated outbreaks, predominantly through the Middle East, but also in South Korea. And then, of course, we know in the background what used to be called 2019 novel coronavirus and is now called SARS coronavirus 2 emerged in Wuhan, China. So what do we know about coronaviruses and their transmission? And this kind of goes back to a lot of the media that I've been doing as of late, and a lot of the debates that I found myself a part of. Where do coronaviruses come from, and how do we know that they're coming from nature? Well, if we look back at coronaviruses, coronaviruses affect a broad number of different species, so that includes humans, but also animals. But one of the things that we know is that bats actually act as a pretty good reservoir for a number of coronaviruses. And what that means is basically bats. As much as I love them as animals, and I think that they are unbelievably cute, especially the giant flying foxes, they are also essentially a perfect virus machine. And we're still getting into, I guess, a more thorough understanding of why that is. But what we do know is that bats basically can allow, various emerging viruses to essentially persist within their tissues for long periods of time. And we don't quite understand why. We don't understand why, that occurs in bats. But yet, when that virus spills over to other animals or to humans, that we see, either some sort of disease symptoms or in case of humans, often severe or fatal disease. So basically, coronaviruses are circulating in bats. We know that they continue to circulate. Peter Daszak and EcoHealth Alliance did some recent studies in China, basically showing that there were numerous coronaviruses that are circulating in bats. And in fact, if you look at villages that are close to bat roosts, they were finding that there was anywhere from 2 to 3% of the people in those villages were becoming seropositive or seroconverting for exposure to coronaviruses. And what that means basically is that these coronaviruses are spilling over into humans that are living in close proximity. So these things are occurring in real time and will continue to occur. 2002, we saw basically the spillover of the original SARS coronavirus, or SARS classic, as Dr. Angie Rasmussen likes to call it, into palm civets and other animals that were traded in live animal markets. So that was, basically the first spillover into animals, and then subsequent transmission from the animals into humans occurred. And once it basically got into humans, then we primarily saw transmission in hospital settings where the virus was able to transmit to other humans and ultimately led to about 10% case fatality rates. MERS coronavirus in 2012 was a little bit different. What we think has happened is that the virus probably spilled over from bats, around 3 decades or more ago into camel populations in the Middle East. And basically the virus started to circulate within camels. In camels, what's been found so far is that MERS coronavirus produces a very mild illness. So basically, camels get essentially like a cold and basically get the sniffles. And what they think is happening is that people that are camel trainers or are in close proximity to those animals are actually getting exposed. And ultimately, the virus flips over, gets into humans, and then again, through transmission, largely in hospital settings, we see that MERS causes up to 40% or 30 to 40% case fatality rates. So it's a pretty devastating disease, but we don't see sustained human-to-human transmission for either the original SARS coronavirus or MERS coronavirus. Before we get into SARS-CoV-2, I'll quickly talk, just to give you kind of a Cliff's Notes version of the life cycle. We've all heard of the ACE2 receptor, so I'll just give a little bit of perspective. So basically, the virus, or coronaviruses in general, we think are largely, brought into to humans for infection through respiratory droplets. And basically, those viruses, in the case of SARS coronavirus or SARS-CoV-2, attach to the ACE2 receptor on specific cells within the respiratory tract. For MERS coronavirus, it's a little bit different. It's a different receptor called DPP4. But what that does is it basically is a specific interaction that causes the virus to attach down to the cell, and that basically causes the cell to pull the virus inside. And once it gets pulled in, basically there's an uncoating process in an organelle called an endosome, which basically we normally use, our cells use to basically sample the extracellular environment, and it basically becomes very acidic and it breaks down different byproducts. But in this case, the virus gets in and essentially it opens up and basically releases its RNA genome into the cell, into the cytoplasm, and that's where we start getting the production of both new viral proteins as well as new copies of the viral genome. And ultimately what happens is that the cell will produce more virus, and those viruses get released and then infect subsequent cells. So really, when we talk about ACE2 and this idea of targeting ACE2 as a potential, a potential way to identify therapies. That's what we're talking about, is primarily to try and block this initial uptake of the virus into cells. So let's switch gears completely and just talk specifically about COVID-19. So basically on December 31st, 2019, there were initial reports that came out on basically ProMed email on that evening, talking about a SARS-like illness that had been identified in China. And this was in Hubei province in Wuhan. And basically what they said was that there was a cluster of atypical pneumonia cases that were exhibiting signs similar to the original SARS illness. And all of these cases were linked to, or potentially linked to, a live animal market. And that kind of, got basically the scientific community on social media, pretty, I don't want to say, pretty concerned, but I think it kind of flipped the switch a little bit from being an interesting observation to being something more along the lines of this could potentially be something much larger. And the reason being was this link back to SARS. SARS had disappeared essentially at the end of or mid 2004. We have not seen any cases in basically the 15 years since then. So for it suddenly to emerge, that was a big concern, because we knew that that virus had spread fairly well with fairly good case fatality rates, in the early 2000s. And I kind of put this up all the time, again, not because I feel like that started to tweet and talk about this, but to give you an idea of the conversations that were happening. December 31st, so on New Year's Eve, the other Dr. Kinderchuk in my house was much smarter and much more talented than I. Her and my 19-month-old called it early for the evening, and basically I saw the initial tweets that came up and started talking to Dr. Megan May, who's also an emerging virus expert. And this was one of many conversations that were going on across the globe of saying, what is going on? Is this something new, or is this SARS coronavirus again? Well, what do we know now? Well, we know that this was something new. In a matter of 5 months, the virus has spread from China outwards across the globe. So we've seen, obviously, Europe had been hit hard throughout February and into March, and then of course the virus got into North America. Canada initially looked like we were going to take a pretty tough hit from it, with cases in British Columbia as well as Ontario and Quebec. But we haven't had the kind of borne the same brunt of COVID-19 as what the U.S. has, and I think there's various reasons or variables behind that, including just the low population density that we have in Canada based on our geographic distribution of people. But what we do know is that this virus has spread everywhere across the globe, and as we're starting to see cases clear up in some regions, we're starting to see potential signs of potential second waves starting to crop up as well. And for us, this is a big concern. We're a population that has no pre-existing immunity. We have no vaccines and we have no therapeutics. So we are somewhat at the behest of this virus right now, unless we can actually try and just essentially curb transmission by not giving the virus the opportunity to transmit from person to person. And this gives an overview of, really what the data look like. Like I said, I was in Kenya during mid to late January for 3 weeks. We were talking at that point as a classroom about COVID-19 and potential concerns within Africa, because we knew that there was a lot of Chinese trade that was going on with in other regions across Ecuador. And cases were starting to spike. Now, in this time frame, I don't think we expected this. I think we knew that there was something unique going on, but we didn't see the immediate spread to Europe that I think maybe we had somewhat anticipated. And I think we thought at this point, as cases started to kind of trail down into February within Wuhan, I think we started to think, okay, maybe we've actually dodged a bit of a bullet here. And then, of course, we know that cases took off through the Middle East and obviously through Europe and in Italy, and then got into North America and have been just devastating for public health and global economies. So what do we know at this point? Well, I think, listen, I know that there is still some discussion about what the origin is of SARS coronavirus 2, and how confident are we that this was an engineered virus? I'll just put a caveat: it was not. And how confident are we that this was not? And at least all the data so far that we've seen suggests right now that this simply was a spillover of a bat coronavirus. And it matches the pattern of what we've seen coronaviruses doing for their history as well as for other emerging viruses. So we're pretty confident that bats are the reservoir. We don't know about intermediate animals that are involved in this. So that is a point of very heavy research right now. What we do know is that the virus primarily is being spread by respiratory droplets. And so this figure by Dr. Ian McKay kind of gives a good summary of how the virus is being spread and overall the distance at which the virus can be spread. So we don't think that it's being spread by small particle aerosols, unless we're dealing with things like intubations, where healthcare workers would be in very close proximity to patients and actually using procedures that would cause aerosolization of the virus. So we know that social distancing can ultimately basically remove that ability of the virus to simply be able to do what it does in terms of its transmission. I get a lot of questions about COVID-19 and influenza, and that's because I work with viruses, and a lot of people, when we think about pandemics and even epidemics of respiratory viruses, the easiest comparator is to go back to influenza. We had unbelievable tolls on human health and global public health for over a century now, and even longer. And that, of course, we always use 1918 as kind of the benchmark of 50 to 100 million people ultimately succumbing to that disease. When we look at seasonal flu, though, we have to keep in mind that seasonal flu still kills about 500,000 people across the globe each year. So when we do these types of comparatives between viruses, I think often we get in this case of saying, well, COVID-19 is just like seasonal flu. And I keep saying, yeah, but seasonal flu is really bad. We've just become accustomed to think that seasonal flu is just something that happens. And we know that ultimately, if we were able to increase vaccination rates, the likelihood is that the toll of seasonal flu, especially in high-risk groups, would be much less. But when we compare the two viruses, so when we compare seasonal flu strains, whether they're H1 or H1N1 or H3N2 versus SARS-CoV-2, which causes COVID-19, the first thing is the R0 number, so the number of people that could be infected by an infected person, is quite different. For COVID-19, at the time of this writing, it was estimated about 2 to 2.5. We've seen in some places, in some situations, it can reach up to 6. So it's definitely more transmissible than what we see with flu. So that creates a bit of a problem for us because of the fact that ultimately it's just spreading to more people. The incubation time is much broader than flu. So people, when they get infected, will exhibit symptoms from influenza very quickly, within 1 to 4 days. For COVID-19, it's much more broad. So 1 to 14 days, predominantly around 5 or 6 days post-infection is when we see symptoms. And in about 98% of the population, they'll see symptoms by day 12. But that leaves a large period of time where that virus is incubating within a person. And now that we know that pre-symptomatic transmission, so transmission when a person is not feeling ill, but has virus within the respiratory tract, can occur. So now, it makes it a lot more difficult to say, well, when can we start to identify COVID-19 patients, and how do we go through and test and identify all those pre-symptomatic folks that are potentially able to transmit virus? Hospitalization rates are very different. COVID-19, when you look, again, we talk about seasonal flu, as being, something that kills 500,000 people a year. It puts about 2% of people in hospital. COVID-19 so far is about 19%. It'll probably become less so as we start to get a better idea of how many people it's transmitted to, but it still is putting a lot of people in the hospital. And the case fatality rates definitely vary from region to region and situation to situation, but what we can say pretty comfortably is that for COVID-19, the case fatality rates do appear higher. what creates a bit of a problem for us when we start to think about things like, trying to diagnose or trying to identify COVID-19 patients and transmission in communities is that ultimately what we have is basically a delay between the time that people are actually getting infected and displaying symptoms as compared to when they're actually getting So what ends up happening is that we actually have, basically this break or this time lapse between the point of somebody being infected and potentially transmitting virus versus when they're actually being tested. So I know that the figure is ultimately, it's very busy, but this time lapse creates an issue for us because what we're seeing when we see case numbers is that those case numbers represent what happened in the past. So what we have to think about is the fact that as we start to implement new procedures, or we start to do things like changing social distancing parameters, like we've done here in Manitoba this week with our kind of first phase of opening up social distancing measures, we won't see the effects of those events for probably somewhere between 7 and 14 days. So that makes it a little bit harder to try and predict what is going on with this virus, and again has put us fairly far behind the 8 ball at being able to understand what our actions are going. When I was in Kenya, and cases started showing up in China, and we started hearing some of the clinical data, or started seeing some of the clinical data that was coming out of China. Basically at that point, the story was centered around the fact that the majority of deaths and severe cases were predominantly related to people that were seniors or that were quite elderly or health complications. So I think at that point the story became it's basically a disease that affects a very small segment of the population. Everybody essentially under the age of 65 it will be fine, that they won't get they won't show signs of disease, or they will have very mild disease. Well, the story's not quite that easy, because when we look at data coming out of the CDC down in your neck of the woods in the US, when we look at hospitalizations across all of the different age groups are actually pretty similar, until you get into the more senior populations, where actually death starts to take over in ICU, care starts to become higher. But in the earlier age populations, we're seeing a lot of hospitalizations, and that creates a bit of an issue, because the fact is that there are a lot of people within this age group, I'd say between 20 and up to 65, that seem to be somewhat under the guise that they are impervious to SARS-CoV-2, and that has put us into a tough position, because these ultimately will be people that will overwhelm the healthcare system, and we've seen that obviously in different centers across North America. What we don't know, and we're starting to get a better idea of, is when did the virus spill over. So I've said at the very start of this that everything with the initial cases was linked back to a single seafood market or animal market in Wuhan, China, that basically stemmed from an animal market. What we found subsequent to that are cases that were actually positive for SARS, no relation to that animal market or to people that were at the animal market. So this starts to suggest that this virus was likely transmitting for a longer period of time in the background, and we've seen recent data over in the past couple of weeks to suggest that it could have been back probably closer to mid-fall that the virus was circulating under the radar. Where did the virus come from? There's the golden question. So we have a pretty good indication that the virus spilled over from bats. Has about a 96% sequence identity to a bat coronavirus. So that gives us pretty good indication where this virus came from. But we're seeing some similarities with other coronaviruses in animals like pangolins. So it starts to suggest that there might be intermediate animals that we need to take a look at, that the virus might be circulating through, and may actually relate back to the live animal markets. We've also recently seen that transmission from humans to cats as well as mink has occurred, but that transmission has all been one direction. So we have not seen basically unidirectional transmission of the virus from animals back to humans. But it gives us, again, some data to start to look back at the origin story for this virus. Out of transmission, I think pretty safely can say that we think that everything is related back to predominantly respiratory transmission of the virus. We have found some indications of potential virus positivity in stool as well as in urine, but there's still a lot of questions as to whether or not there's infectious virus within those fluid samples. There's actually a story that I have yet to read today talking about potential virus positivity in semen, which is quite interesting for me because of the work that I do with Ebola and Ebola persistence and sexual transmission. So we will get a better picture of what's going on with transmission as we start to roll through more of the clinical data, predominantly from here in North America. Reinfection. So we've talked, we've heard a lot about reinfection as of late. We don't think reinfection occurs. So with animal models, predominantly non-human primates, basically non-human primates that are infected and recover from disease, so far what we've seen is that they can't be infected. So it gives us some idea that animals, are basically and of course we heard stories about people that had negative and then became positive after recovery. Well, we think that actually that has to do with limited detection with the diagnostic assays. So essentially, if you are testing low enough amounts of material, you basically get to a point where it's essentially a coin flip, whether you're going to be positive or negative. So a lot of those tests we think are basically just false positives. Protective immunity, we're getting a better idea of right now. So there's been a lot of discussion about whether or not people that are, recover from infection or who have been infected. And we know that right now it looks like the virus actually only transmitted in some cases through 2 to 3% of the population, which means that a very low number of people were infected in this first wave of COVID-19. So we're nowhere near herd immunity for this virus, but we also don't know if these people are actually protected. So even if they seroconvert and they produce antibodies, will those antibodies protect them from subsequent disease? Well, what we do know and we have some evidence for is that if you take convalescent plasma from recovered patients, and if you treat patients that are severely ill with that convalescent plasma, they actually recover faster than patients that are not treated. And that starts to suggest that there are antibodies or factors within those recovered patients that provide some amount of protection for the virus. So the story is not clear yet. The data certainly remains variable in humans, but I think we're getting better indications of what the profile looks like. And the last slide I'm going to really kind of mention is this whole idea of distinguishing misinformation. From January onwards, I've been involved in a ton of media talking about misinformation with this virus, and that's gone everywhere from the potential links to 5G networks to potential links of this virus with assertions and engineering. And I wrote an article on this for Forbes as my very first article, which led to a lot of emails coming to me personally, questioning why I believe nature over any of these conspiracy stories. And ultimately, what we have to do is go back and say, from a scientific standpoint, what do we understand about viruses? And really try and get, from a science communication standpoint, this information out to the general public. Because the unfortunate side is we are dealing with the first pandemic in the age of social media. And what's happening right now is that these conspiracy stories spread essentially virally as quick as the virus itself. And it's difficult for us to counter this when only a few people are kind of trying to lead the charge in basically disrupting these misinformation chains. So that's kind of where I sit now. We're doing a lot of research. I didn't talk about that because I think it's more important to talk about just COVID-19 in general and discuss the things we do and don't know. Always have lots of people to acknowledge, but always want to acknowledge my international to work with, particularly those in Africa, including on COVID, as well as all of my collaborators. And thank you.
Great. Thank you so much, Jason. Very much appreciate that. Let me pull the presenting rights from you so that you get a break relative to your screen, and ask folks, we've got 10-15 minutes or so here, whether people have some questions. Please feel free to type them in and ask them. We'll note via chat, I already have a few, so I'll start with those. The first question that's been asked is around whether we as ILSI North America plan to have recorded this and make this presentation available. So let me start by confirming that yes, we have recorded the presentation, and we will be working to post this on the YouTube channel so that if colleagues that you work with were not able to join us today, that they certainly will be able to join us today. Second question I had come in was related to, let's see, let me pull this up. Whoops. Second question I had was related to how, and I know we heard some different things here, but second question I had was a bit more for Trevor, wherein, if I understand the question, you showed, Trevor, 3 different equations under that SARS model. And the question was, if there is a case, if it's worth modeling, if it proves to be worth modeling, that somebody can go from that R group, from that quote recovered group, right, and become susceptible again, does that mean that there's a 4th equation that comes in, right? And then I think it might be worth, Jason, to have you kind of comment on that, comment again on the chance of reinfection. So.
That's great. Gwendolyn, are you able to push it back to me so I can literally share a slide that answers that exact question?
I actually can do that. As soon as I click the right button. Let me make you the presenter again, Trevor.
All right, and I have to make sure I got the right one. But so the question was a great one, and to restate it, just to make sure we're clear, the question I believe was about if people who are recovered could go back and be susceptible, which is Jason was just sort of finishing up in his talk, was discussing at some level that possibility. So from the level of the modeling of what that happens, basically, if you recall, these equations were the original 3 equations. And what we're trying to say is that some portion of people who are recovered could end up back in the susceptible camp. And so basically what I do is I just subtract some portion from the recovereds and add them back directly into the susceptibles. So it's not like a 4th category of person, it's just that some percentage C of those recovered end up going back into the susceptible camp. So that's how I would typically deal with that particular thing.
Great, thanks, Trevor. So I'll kind of throw in my 2 cents on this with what we know and where our knowledge is at. So what we understand is, first of all, this virus has really been around for about 5 months. So we're just now starting to get an appreciation for what the immune response or the protective immune response looks like in humans that recovered, in particular those from China in January. And so we're still in this position of kind of inferring what we think happens for this virus, but we can pull back a little bit from what we understand with SARS coronavirus and MERS coronavirus, where we saw that long-term immunity or protective immunity lasted somewhere in the category of a few months to a few years. So the truth is we don't know right now. We especially do not know how immune protection or antibody development relates to disease severity, which there have been some question marks as to whether people with milder cases have a lower amount of protection than those that have more severe cases. What I can say is stay tuned. We're definitely through some of the work that we're doing in ferrets right now, and others that are working on things like non-human primates. We're getting a better indication of what we think is going on, but we certainly are not at a stage yet where I think we fully understand, the length or anything about the duration or the strength of protective immunity.
Fantastic, thanks. It's I'm looking at the question box. They're now starting to light up here on my end. I'm going to note out of hand that I'm reading them and looking to combine them. One of the questions that I think is very relevant is what's the evidence, and Jason, this is not looking to put you on the spot, right? But what's the evidence around transmission by touching surfaces, right?
Yeah.
Because and if you want to comment on COVID-19 directly, great. But if you want to talk about coronaviruses more broadly, that would be
sure. Sure. So we know with other coronaviruses and other respiratory viruses that they can be transmitted through direct touch. And again, it's direct touch back to mucosal membrane, so our eyes, our nose, our mouth. What we don't know for COVID-19 specifically is if you touch a surface, how much infectious virus has to be on that surface at that time for you to basically touch it and then touch yourself and get infected. So essentially, what is the infectious dose of virus that is required to produce disease in a person? Those are the questions we have no idea on right now. I've heard very, very rough estimates and more so guesstimates from people talking about probably hundreds to thousands of individual viral particles that would be required, and that's just based off of information that has been seen in the past with other coronas. With the animal experiments right now, we'll get a better idea of what levels of virus have to be administered, in particular to non-human primates, but we don't know at all what that infectious dose actually is.
Great, thank you, Jason. Another one that's probably a little bit more for you, Jason, is why is it that novoviruses cause foodborne illness, but coronaviruses cannot? I think it's a high-level question, but I think that's very foundational and would be good.
No, it's a fantastic question, right? So, why do people when they go on cruise ships get sick by noroviruses all the time? Yet, we know that coronas, obviously, COVID-19, gone on to cruise ships as well, but it's not as common, right? And we don't see nearly as much transmission. It all comes back to the nature of the virus itself. So coronaviruses are what we call enveloped, which basically means that they are surrounded by a layer of fat or lipid that basically they take with them as they basically are released from our cells. And the downside of that lipid for the virus is that lipid can actually be disrupted fairly easily. So whether you use things like ethanol or even UV light or different chemicals can break those apart. But we also know they're not very hardy. So what happens over time and actually fairly quickly in a lot of cases, is that basically those lipid membranes are not very stable and they split apart. Non-enveloped viruses, so things like the noroviruses, they actually last a lot longer because they don't have that same kind of fragility as what the envelope viruses do. And that basically allows them to essentially persist for longer periods of time and also be more resistant to things like acids or pH changes. So that's why when we look at noroviruses, they last for so long in food sources. They're able to be transmitted easily. They last on surfaces for a long period of time. Coronas just don't. So we have concerns that within about 24 hours, that kind of initial period that coronas can likely remain viable on surfaces, but after that, they'll fall apart. And that's the same thing with influenza and same thing with Ebola. That they actually on a surface they're not very hardy viruses, and that's kind of as simple as I can make it.
Great, thanks, Jason. last question, because I want to be respectful of everybody's time here. So is around reports that the virus is somehow different due to different severities being seen in China versus parts of Europe versus the US versus Canada? Or is it all the same virus, or are they different, right? Is there a difference in infectivity and severity, I guess, is another way to ask that question.
Trevor, do you want to add anything in before I do?
No, go ahead, please.
Okay. So this story kind of took off, I think, especially with the LA Times article yesterday, and sorry to name drop on specific news agencies, but there was obviously a lot of reports talking about mutations, and this idea of whether or not mutations are basically causing differences in virulence and transmissibility of the virus. So what I will do is I'll take a step back and say, right now, viruses, especially RNA viruses, they will mutate over time. That's the unfortunate side for them, is even with something like a coronavirus where they have proofreading capabilities, so they have that spell check, they still mutate because they produce millions of copies of themselves and they're somewhat inefficient. But often those mutations don't mean anything. And we saw this with Ebola in 2014, where we saw basically mutations in the protein that sits on the virus surface. And there was a lot of discussion about whether or not that meant anything in terms of changes in virulence. And ultimately, what they found was no, it didn't mean anything. We've seen some discussion recently about changes and a specific change in a very specific amino acid in the spike protein on the SARS coronavirus 2 virion. But all information that we have so far really does not suggest that we're seeing differences in patterns of transmission or patterns of virulence. And that's not to say that over time we won't find out that there is something different. We have to do quite a bit of biological validation of those observations, do analyses within the laboratory and animal models to see if there are differences. But I think what it's going to come down to, and this is just my own simple virologist standpoint, is that some of the differences we're seeing in transmission and virulence are likely more related to other variables in populations. So here in Canada, we have a very, very high case fatality rate and total number of fatalities in long-term care facilities. And that's because the virus was able to get into those areas and really decimate those populations. In other regions, it's going to be different. And we look, places like low and middle income countries in Africa, where we thought we would see devastating numbers of fatalities, we haven't seen that. So now the question becomes, is it something different? Is there epigenetic factors that are different between the populations, or is it just overall differences in health? I think we'll find out as the months roll on, as people analyze through the data. But all suggestions at this point are that the virus basically is essentially behaving the same way that it did when it first emerged in Wuhan.
Great, thank you again, Jason, for that. Realizing that we are coming up against our time limit, I want to thank the attendees and our ILSI North America members from the public and private sector for their engagement today in this webinar. I want to especially thank Trevor and Jason for their time, their energy here today. Trevor, I think the slide in particular that you showed, which demonstrated how social distancing impacts the variable alpha, right, and versus quarantine hitting different numbers. I think that is, at least for those of us who are math geeks, very comforting to sit there and go, oh, okay, now I get how it works, right? So thank you very much for that. And Jason, thank you very much for taking the time to walk all of us through, why and how SARS-CoV-2 has come out as such an impactful virus on us on a biology level. So thank you for that. So with that, want to wish everybody a good rest of their day, and thank you again for your time and your engagement.